Okay, I'd like to thank the organizers for inviting me. It's so nice to be in virtual Frankfurt. The last time I was in virtual Frankfurt, I never got out of the airport. Okay, so I want to start by reviewing single integrals, both classical and tropical. So the classical case, we're going to just be talking about a Riemann surface. So we're going to only be talking about the one-dimensional case here today, and X is going to be our Riemann surface, and omega is going to be either a holomorphic or a closed one form, and gamma is going to be a path in our Riemann surface. And we can just define the single integral by pulling back the one form by the path and integrating it. Now, there's a combinatorial analog introduced by Mikhalkin and Zarkov, and here gamma is going to be a metric graph. I'm going to switch back and forth between metric graphs and like combinatorial graphs, where you would think of every edge as having length 1, probably without telling you. And eta is going to be a tropical one form. So what is a tropical one form? The data is going to be a real number attached to every directed edge of the graph, such that if I reverse the edge, it reverses the real number. So I guess you should think of it as really being on a given graph, it's eta e dt, where t is a parameter for the edge.
Just a word, is the are the slides moving for everyone else? Because for me they are not moving.
No, it's for me as well.
Oh, ooh, here we go. So,
very good.
Okay, this works now.
Yeah, something weird happened. Okay, it clicked on the wrong thing because I'm me. All right, so the data is going to be a metric graph and then a tropical one form. It associates a real number to every directed edge, so that when I reverse the direction of the edge, it reverses the real number. So maybe you want to think about this as eta of e dt as this one form on the edge, where t is a parameter for the edge, such that the etas obey the harmonicity condition, which means if for every vertex v, I look at the edges adjacent to v directed away from v, and I sum eta of those and I get 0. And this is on the nose, the first homology of the graph. But I kind of just want to use etas. I want to use tropical one forms because it makes the analogies better. And then for a path in the graph, which I'll just list as I'll view as a list of edges, integrating along that path is just summing the etas of each edge. And if you're in the metric situation and you only have like sum of an edge, you just multiply by the length of that edge. So actually, I guess since I'm talking about the metric case, it really should be that. And I will denote tropical one forms by omega 1 of gamma. And I can view tropical single integration as a pairing between first homology and tropical one forms and with target real numbers. And I can also interpret this as a pairing on H lower one on first homology, because this is isomorphic to first homology. And then this is the cycle pairing. So the cycle pairing is the pairing on first homology induced by the Kronecker pairing on edges. And that's just a fancy way of saying if I have a pair of cycles and I pair them, it goes to the signed length of their intersection. So meaning an edge counts positively if the orientations agree and negatively if they disagree.
Eric, at that step, is there a reason why you want to restrict integration to cycles and not allow integration along chains?
No, I'm fine with chains.
Okay,
like I'm just careless.
Thanks.
And I'll switch back and forth between paths and cycles. So in this particular, here's an example if like gamma is this path and eta is this one form, that's just one on this cycle, meaning it corresponds to that cycle. Since the orientations disagree and they intersect in two edges, you get a -2. All right, and I'll talk about applications, and I'll be talking about these applications in various contexts. So one is the tropical Torelli theorem, which is due to Caparassa and Viviani, and I should also mention the work about Tamkin, which says that the data of first homology with the cycle pairing remembers bridgeless graphs up to an equivalence relation called two-isomorphism. All right, another application, and this dates back to Picard-Lefschetz, and it was Picard and Lefschetz, but it's put in modern form, probably in like SGA 7, is the monodromy pairing. And I'm going to talk about a very classical way of thinking of the monodromy pairing. So I'm going to have a family of Riemann surfaces, script X over a disk, such that it's smooth when t is not 0, and over the origin it has nodal singularities. And then I'm going to let omega t be a family of one forms that extend to the total space in a particular way. And yes, yeah, I'm talking to the people. I'm talking to them about integrals. And then gamma t will be a family of paths. And I could study the asymptotics of this single integral. And when I'm degenerating the Riemann surface forms nodes, which means they're locally given by xy equals t, and then my one form grows poles near the node. And what happens, at least if I require it being like have nice extension properties or be a section of the dualizing sheaf. And when you integrate through the node, or you're going through a path that I guess passes through a vanishing cycle that's going to shrink to 0 on the node, the contribution is a log t, where a is picking up the residue of this pole. And if you want to think classically, this is like the thick, thin decomposition of a Riemann surface. Or if you have a family and you're thinking about like monodromy of this family, this corresponds to a Riemann a Dane twist, where you're shrinking the vanishing cycle to 0 and it's twisting a path through the vanishing cycle around it. And you can take this situation and you can tropicalize it. So your omega t's give you a tropical one form eta, and your path gamma t, it becomes a path in the dual graph. So it becomes a cycle in a dual graph, which gives you c. And the coefficient of log of t, so the asymptotics of this integral are the worst thing that happens is it's log t as t goes to 0, and the asymptotics, or the leading term is controlled by this combinatorial term. And this is related to the monodromy pairing. It's an analytic way of thinking about it. And the fact that the tropical one form is coming from the residue gives you some justification for the definition. So this harmonicity condition is just the residue theorem for one forms. All right, now I should probably pause for questions. Okay, and then the third application, the one I'm particularly fond of, is p-adic integration. So I'm going to take a finite extension of QP, and I'm going to have an algebraic curve defined over that field. And omega is going to be a regular one form on the curve, and I'm going to have points P and Q on the curve. And I want to integrate a path between P and Q. All right, now I know what you're thinking. What does it even mean to have a path in the p-adic world? And there's a notion of path due to Berkovic, like because Berkovic spaces actually have reasonable topology. But I'm not going to talk about Berkovic spaces. I'm just going to use some very primitive notions of dual graphs. Okay, so I'm going to talk about these two notions of integration. I call them abelian and Berkovic-Coleman integration. They're the same on good reduction curves. meaning if you extend your curve to a family over the DDR, over the closed fiber, the curve is smooth, then that's good reduction. But these two notions are different over bad reduction. So the first notion is abelian integrals, which are path independent. So these are integrals from a point P to a point Q. And these are important in the Chabati method. And the way it's defined is the following. So you have your curve, you map it to its Jacobian by the Abel-Jacobi map, and then you take the log. And the amazing thing is, p-adically, the log is a single valued function. It's not an analytic function, but it makes sense everywhere in the Jacobian. You don't have to worry about it, like about monodromy in the usual sense here. And now the log lands in the Lie algebra of the Jacobian, but the Lie algebra is dual to one forms, so I can evaluate on a one form. So this composition is abelian integration. And it's somehow very global because it requires the Abel-Jacobi map to define. And it was the insight of Coleman is that you could do this integration locally on the curve. And this is done through so-called analytic continuation by Frobenius, or the Dwork trick. And that was pretty amazing insight. And I'm going to talk about an extension of this integration theory to bad reduction curves. And it was given final form in Berkovic's book on p-adic integration, although there's hints of it in this paper of Coleman and Deschalit. So what we're going to do is we're going to take a semi-stable model of the curve, and I'm going to let gamma be a dual graph of the curve. And I'm going to have the points P and Q that specialize to components of the dual graph V and W. I'm going to pick a path gamma in the dual graph from V to W. And what I can do is I can define the Berkovic-Coleman integral by piecing together p-adic integrals locally. So essentially what you do is you cover your curve by basic wide opens and annuli. So basic wide opens are certain subsets of a good reduction curve, and then you can do usual p-adic integration on them. And then annuli are like p-adic annuli, and they would be given by like the absolute value between two values. And then when you integrate one forms, well, you can nearly integrate them term by, you can expand things in power series in your parameter, and you can nearly integrate them term by term. The only issue is integrating dz over z. dz doesn't have a classical integral. So what you would join a branch, what you do is you would join a branch of logarithm log z. And then once you have that branch, you can piece together the integrals. And then that will involve a log z in, or a log of some number in the answer. And you should really think of it as being very similar to the situation of degenerating families of integrals on degenerating families of Riemann surfaces. Okay, so this abelian integral is the integral we want. The Berkovic-Coleman integral is the integral we can do. And there's path dependence here. So how do I compare these two? Because I really want this guy. All right, so I start with an observation that this guy has periods, this guy doesn't. And I can, but they're both integrals, so they should be given by anti-differentiation locally. You can prove that. And so if I look at their difference is going to end up being some combinatorial object. And let me give an ahistorical way of doing the comparison. It's some combinatorial object. So maybe it's given by a tropical integral, and then by non-degeneracy of the tropical integration, it should be determined by its periods, and then you can just guess the answer. And so let me rephrase the comparison theorem. So what I'm going to say is you're going to take cycles in your dual graph, a basis of cycles, and then you take a dual basis of tropical one forms. And then it is a theorem with Joe Rabinoff and David Zurich Brown, as described or as rephrased in a paper with Eniskaya, that the difference is given by this expression. So let's try to read this off. I'm integrating between points P and Q. And for the Berkovic-Coleman integral, I'm doing that through a path gamma in the dual graph. And I want to compare that to just the abelian integral between P and Q. And it will involve periods, p-adic periods of the curve. These are these Berkovic-Coleman periods, although like they're similar to things done by Tate and Mumford and Drinfeld and Manin. And these are fixed and don't depend on the path at all. And then there's this tropical integral that depends on the path. And to verify that this formula makes sense, if I set gamma to be a path whose underlying cycle is Ci, I get that the Berkovic-Coleman integral is equal to, this is the period, is equal to this period term on the right-hand side. And this description is ahistorical. It was actually proven through an analysis of the Raynaud uniformization of the Jacobian. But morally, I like to think of this as what's happening. And this comparison was also given by Mikhail Stoll and Amnon Besser and Sarah Zerbs. All right, so that's it for single integration. So are there questions about this part of the talk? Because now I want to talk about iterated integrals. And these are due to KT Chen. So the setting is going to be the following. I'm going to have a Riemann surface, and I'm going to need a base point here. And I'm going to have one forms omega 1 through omega r. And I think I want, at least want them to be closed. I probably want them to be holomorphic. And I'm going to define an iterated integral. And I'm going to define them recursively by primitives on the universal cover. And here the paths will all be based at the point x0. So I lift x0 to a point living above it in the universal cover. I take the primitive of the first one form. So that's just single integration. Then I take the result of that, I multiply it by omega 2, and then I integrate again. And that's the expression I'll denote by the integral of omega 1, omega 2. Then I take the result of this, I multiply by omega 3, and then I integrate again. And so these lead to iterated integrals. And these depend on more than just the homology class of gamma. They depend on the unipotent bit of the fundamental group. So what's really happening is you're interpolating between homology and the fundamental group. Like, so such things like single integrals in the classical sense descend to the universal abelian cover, the abelian universal cover. These guys live on, I guess, the unipotent universal cover, like where you're chasing through the lower central series. All right, so let me give you some properties of these guys. So first, there's a concatenation formula. Now, it shouldn't be simply additive, because otherwise it would descend to the fundamental, it would descend to homology. So the concatenation formula is pretty involved. We've got gamma 1 and gamma 2 are two paths we're concatenating, and I read paths from left to right. And what I do is I look at all ways of breaking the one forms in order. So I go from omega 1 to omega I integrate those on gamma 1, and then I go from gamma omega I plus 1 to omega r, and I integrate those on gamma 2. Multiply these together, and I add them up. And then there's a nilpotency property. So if I were to take, if I've got K1 forms, and I've got r greater than or equal to k, this formula is only useful then. And I integrate alpha 1 minus 1 up to, or I integrate along the path alpha 1 minus 1 up to alpha r minus 1, which means I multiply, and I guess I want these to be loops. and I multiply these out and I evaluate linearly, then if I have more loops than I have one forms, I get 0. And if I have exactly the same number of loops as one forms, I get just the product of these usual integrals. Here, I'm pairing omega 1 with alpha 1, just integrate up to omega k with alpha k, and I multiply out. And this fact lets us show that, in a certain sense, iterated integrals is non-degenerate. All right, and fact 2 lets us encode iterated integrals algebraically. So I talked about chasing through the lower central series. There's a systematic way of doing that using the group ring. So I form the group ring, which are just formal. I'm going to do the real group ring. These are just formal, real combinations of elements of the loops in the fundamental group. And then I've got an augmentation map, which just sums the coefficients. And then I have the kernel, which is the augmentation ideal. If I quotient by the augmentation ideal, I just get the real numbers. If I quotient by the square of the augmentation ideal, I get the real numbers direct sum first homology. So that's giving me the abelianization of the fundamental group. And integrals of length 1 are linear functionals on this guy. They only depend on homology. And then integrals of length 2 are linear functionals on this guy, on the group ring modulo I cubed. So this remembers a tiny bit of non-abelian data. So here is the group ring modulo I cubed. Here's the group ring modulo I squared. The kernel is I squared mod I cubed, which is isomorphic to first real cohomology tensor squared. So that's homology data, but there's a little bit of homotopy data hidden in the extension data in this exact sequence. And I guess this is related to a lot of Carlson's ideas of extensions of mixed Hodge structure. All right, and then the iterated integrals of closed one forms put a mixed Hodge structure on the fundamental group. And this was noted by Morgan and then by Hain. And then cool fact is there's a version of the Torelli theorem in this setting, which says the mixed Hodge structure on the fundamental group modulo I cube determines the Riemann surface and the base point up to finite ambiguity. So I think this is kind of cool because this is saying this linear algebraic data coming from the extension remembers the base point, which somehow is a nonlinear thing. All right. All right, and now I want to introduce tropical iterated integrals. Questions on the last section? Okay, and I started playing with tropical iterated integrals as a toy model for thinking about iterated integrals because I was trying to understand the non-abelian Chabati method, and they turn out to be cool on their own. And I've since seen things that are similar to them in geometric group theory. Okay, so I'm going to denote them by integral t, and I'm going to have a loop or even a path, and I'm going to pair with L1 forms with the target value being Q. Actually, I think I made the one forms real, so I want the target to be R. And I'm going to define it for paths in my graph. And in here, Lord, I think I probably am. I wrote it down for combinatorial graphs, so I think I need a length term. So what it ought to be is if I integrate a tropical one form or a collection of tropical one forms on an edge, I take each one form, I look at its value on the edge, I multiply them together, I multiply by the length of the edge to the number of one forms, and then I divide by L factorial. And so that's how I integrate on a single edge. And then I can treat a path in my graph as a word on the edges. And then I just use concatenation to add one edge at a time. And then it's an easy verification that if I add an edge and then I take the reversed edge, I get the original integral. So this integration descends to pi1. And it's easy to verify that we've got the concatenation and the nilpotence property. And then just as before, an iterated integral of length L descends as a functional on the truncated group ring of the fundamental group. And here I'm using integer coefficients, and there's a reason that'll become important later. All right. Questions, concerns, complaints? Angry letters to the editor.
So you're pretty much building in the concatenation by definition, right?
That's right. Oh, right. I'm doing it edge by edge, and then, right, it's an easy induction to show that it holds for arbitrary concatenations. Okay, so the first application is the tropical Torelli theorem, which is with Raymond Cheng. And it's analogous to the Hain and Pulte result, but it's a little bit unsatisfying for reasons I'll describe in a sec. So what I can do is I can package the iterated integrals as truncated group ring with the integration operation. And now notice I don't have tropical 1 forms in this data. And the reason why is I can just take the abelianization of this guy, or I can quotient by I squared and read off the homology, and then I have access to the tropical 1 forms. So I can describe this as like an algebra together with this integration operation where I can pair an element here with an element of, or collection of elements in I modulo I squared. And this kind of remembers base points. So if gamma is a fixed bridgeless metric graph with genus at least 2 and V is a point in the graph, then the cycle respecting isomorphism type of the integration algebra determines V up to finite ambiguity. And here cycle respecting means it's an isomorphism of this guy that induces an isomorphism on the first homology with coefficients in F2. And this is the weirdness of this statement is what I have to do to deal with the issues of 2 isomorphism. And the idea is given any 2 base points, or sorry, given base points V and W, there's only finitely many cycle respecting isomorphisms between these algebras. And then once we pick an isomorphism, knowing V on this side and the isomorphism determines W. And that's proven by messing around with the concatenation formula to get a description of the tropical Alba-Jacobi map at the base point. So it's like a page of algebra. It's not deep. I think it's kind of cool though that this data tells you the base point. All right, but I think more is probably true. I think for bridgeless graphs that of genus at least 2, the integration algebra determines the graph together with the base point. I think it does get rid of it's a conjecture, but I think gets rid of the 2 isomorphism ambiguity. All right, and I've spent a lot of time trying to prove this. I can't prove it. But I think I can derive this from the following conjecture. So here, the conjecture says that if gamma is a 2-connected graph, I probably want it to be bridgeless, there's a non-trivial cycle-preserving automorphism of the integration algebra if and only if the graph gamma is a hyperelliptic graph and V is a fixed point of the involution. Okay, and this is related to a conjecture on tropical Cerace classes by Dan Corey, Ellenberg, and Lee. And it's also the combinatorial analog of a bunch of conjectures about like recognizing hyperelliptic Riemann surfaces based on integrals. And a lot of those conjectures had the form, if a particular class is torsion, then the curve is hyperelliptic. And these conjectures have started falling in the last month. So for just being torsion, these conjectures seem to be false. This is probably the analog of it being two torsion. So this conjecture, the hypotheses are slightly more restrictive. I still think it's true, but now there's a little bit of evidence against it. It would be fun to think about, to tropicalize these papers, giving counterexamples to the algebraic geometric version of stronger forms of this conjecture. It's pretty fun. They just pick curves that have lots of automorphisms, and then even though the curves aren't hyperelliptic, it forces like the Cerese class or whatever to be torsion. Anyway, it's interesting stuff, and this conjecture is incredibly frustrating to work on. I've spent a lot of time on it. I've tried a combinatorial approach, and you just get stuck. Like this unipotent data is somehow so scrambled that you just can't get a handle on it. There's no entryway into it to prove a conjecture like that. And it led to some combinatorial criterion or some potential theoretic criterion for hyperellipticity, which is probably related to Dan Corey's combinatorial condition for hyperellipticity. All right. More concerns, questions, complaints? All right. Another thing to think about is, or another use of these tropical iterated integrals is asymptotics of usual iterated integrals. So you play the same game where you have a degenerating family of Riemann surfaces, and then you have a family of one forms that extends to the family in a nice way. Then the leading asymptotics of this integral is log t to the k, and the coefficient is given by a tropical iterated integral, and that's governed by, so that's combinatorial. So the highest bit, like the worst bit of monodromy, or the worst bit of the asymptotics, is controlled by combinatorics. And this is a complement to a lot of like tropical ideas, because if you had a family of degenerating Riemann surfaces, and you looked at the truncated fundamental group, there's the usual mixed Hodge structure that Hain put on, and then there's additional mixed Hodge structure called the limit mixed Hodge structure. And then the lowest weight bit of this limit mixed Hodge structure is given by tropical iterated integrals. And in some sense, the philosophy of tropicalization is that if you have a limit mixed Hodge structure, the lowest weight bit is combinatorial. So this really is a tropicalization in that sense. All right, and now I want to get to p-adic integration. And I am way crazy ahead of schedule, so please ask questions.
Okay, so Eric, in terms of mixed Hodge structure on the fundamental group and picking out this lowest weight piece, do you expect any generalization to higher homotopy groups?
I haven't thought about it. That would be awesome, though. Like, actually, yeah, I think I would probably expect that. Although things are so weird for anything for dimension 3 and above that I'd be hesitant. Like, okay, so I expect something like that to be true, and it's probably provable for surfaces, would be my guess.
I see. And what are you seeing that's weird in dimensions 3 and above?
Oh, it's just issues with weight monodromy, like p-adic weight monodromy in dimensions 3 and above. But I guess now the situation's a lot better.
And what are those issues?
So, okay, so like okay, so I haven't actually proven the theorem about the lowest weight bit being combinatorial, but it presumably should come from messing around with something like a Steenbrink spectral sequence. And the p-adic analog of the Steenbrink spectral sequence, like, I don't think is, I mean, maybe the situation is now different. I should have asked someone with Schulze's result, but it may not be known. I don't think it's known to degenerate at E2 in dimensions 3 and above. So that would be the issue I'd worry about. Like, I assume everything is good for curves because everything's always good for curves. But I mean, I would like for something to be true, and I would expect it to be true, but I'd also expect it to be really hard to prove, and I wouldn't be surprised if you got stuck.
Okay.
Yeah, but certainly if you're just, probably if you're just messing around with asymptotics of integrals, things work out.
Okay. All right. Thank you.
Yeah. Oh, and characteristic 0, probably everything's fine. Okay. So now let me talk about p-adic integrals. So again, we're going to integrate between points P and Q that specialize to points V and W on the dual graph. And I can define an iterated integral by piecing integrals together. Now, what does it mean to do an iterated integral? Well, you can work out a theory of Coleman functions where you take a Coleman function, those are the functions that arise in single integration, multiply by a 1 form, and then integrate that. And then multiply that by a 1 form and integrate that. And then there's a hierarchy of Coleman functions. And this is the approach taken by Coleman de Chalit and by Berkovic. You can also think about iterated integration as a parallel transport operation. And here, Coleman integration is picking out the Frobenius invariant parallel transport. So this is the approach of Hain and Pulte, who did it in the good reduction case. And then we can start piecing integrals together. And you can also, like, if you have a bad reduction curve, there's something like a Frobenius, or there is a Frobenius on log rigid pi1. So there's a complicated Tanakian pi1, and you can look at the Frobenius invariant paths in it, and you can define integration that way. All right, but these integrals depend on a path in the dual graph. But there's also a single valued integral due to Vygotsky, and this makes use of some monodromy condition. And this is analogous to the abelian integral. It turns out to be equal to it for single integrals. And presumably this type of integration should be important in the Chabati method, and it's important in regulators and p-adic height pairings. So, like, this has been studied in work of Hain and Pulte. So in work with Daniel Litt, we've given an explicit description of the Vygotsky integrals, and this can be turned into an algorithm, which I'm hoping to do shortly. And the idea is to try to pick out a canonical path in the dual graph. Now, it won't be really a path. It's going to be an element of the groupoid module. So it's going to be of the completed groupoid module. So what it is, it's a formal sum of paths between V and W, like taken as a formal limit sum of paths in a certain topology. And this path is characterized by all tropical integrals vanish on it. So if I have a collection, a non-trivial collection of 1 forms, I want to mandate that when I integrate on this formal collection of paths, this formal sum of paths, the integral vanishes. So And these exist by non-degeneracy of tropical iterated integrals. Like they somehow form a perfect pairing. And on a cycle, here's a cycle of length 1. If I have points 0 and x, I can start with a path between 0 and x, and then I have to subtract something off. Something built out of a counterclockwise loop around the cycle to cancel the tropical integrals. Okay, and these canonical paths exist. You can solve for them, and now I can use them to relate Vygotsky integration and Berkovic-Coleman integration. So if I have 2 points specialized into components v and w, and gamma is the canonical path from p to q, then the Vygotsky integral between p and q is just the Berkovic-Coleman integral along the canonical path. And actually proving this, because Vygotsky defines his integral in terms of a monodromy condition, it involves a detailed study of monodromy and Frobenius on the log rigid fundamental group, which is a really big pain in the butt. Who would think that log rigid things would be hard? Okay, and our techniques, like the techniques involved in the canonical path, were already used in the L-adic setting by Betts and Dogra to understand like non-abelian Kummer maps in that setting. Okay, and I will give one example, which is the iterated integral I can work out, which is if you've got a Tate curve, which is k star modulo q modulo the multiplicative subgroup generated by q. So it's an elliptic curve of bad reduction, and its dual graph is a cycle of length equal to the valuation of q. And I want to integrate between the identity and the point x on the curve. What I do is I lift the point x to point in the universal cover, and then I view the integral from 1 to the point in the universal cover as a path. I'm going to integrate the one form dz over z. That's the holomorphic one form on the Tate curve. And so I have the classical integral, the Berkovic-Coleman integral, by the characterization of what it is on annuli is just log of x, but then I have to subtract something off coming from the canonical path. And it ends up being a tropical single integral. And it's defined in such a way to eliminate periods, so it's forced to be this. Like this valuation of x times log of q over valuation of q. And then if I want to do an iterated integral, it's going to be 1 over k factorial times this to the kth power. And you can prove this using a symmetrization formula relating iterated integrals to single integrals. You could probably also try writing down the canonical path. I'd have to stare at this for a while to write down what the canonical path happens to be on the Tate curve.